But yeah, thanks for joining this elite discussion. Yeah, looking forward to it. Much appreciated that you've joined and taken the time. And as I said, if you have any questions, if you'd like to either chat in the chat option there, or come in directly with a question at any point, then feel free. So maybe just a very quick intro round. So I'm Cassie Welling. I'm the COO at Constellar. And I'm moderating the session tonight, but hopefully we won't need too much moderation, and that all of you can have enough content and discussion and questions to keep the discussion going. We've got just under an hour, so we've got 3 presentations this evening. We'll start with Pavel. So we've got Pavel Bordug, who is the VP of Tech Strategy at Carbon Terra, and he was the former CEO of NXT Farm. Pavel, do you want to say a couple of words about yourself?
Yeah, absolutely. So background in remote sensing, of course. Right now working with Carbon Terra. I came out of the University of Waterloo in Canada, so one of the few Canadians here, I would assume. We did a lot of work with the European Space Agency early on, ended up creating a startup called Next Farm, NXT Farm. And we essentially focused on taking satellite imagery, taking remote sensing data sources, throwing them all together and giving farmers the level of insight that they would essentially get while standing in a field. That was the ultimate goal of our product there. We went pretty global with it. We still do have customers in South Africa right now, Brazil, California, all across the prairies here in Canada. And during our process, we met up with one of the big crop input providers in Canada called AgriCity. They were doing a lot of really cool precision ag work, and we joined their sister company called Carbon Terra. So it's been really exciting. We were working a lot with carbon credits in the carbon markets and essentially helping all farmers globally participate in those carbon markets. We're trying to take a sustainable approach where we're taking really research-based way of calculating out the carbon, and then ideally pitching methods to these farmers that they will do indefinitely and are proper sustainable agriculture, so that that carbon that they stored in the soil actually ends up staying in the soil. So as you can imagine, satellite data is a very big component of being able to calculate this stuff out. And thermal, of course, has been something very huge that we used with NXT, as well as currently with Carbon Terra. And I'll definitely dive a lot more into detail into some of those applications later on in this call. Thank you.
Super, thanks, Pavel. We've also got Henk Pelgrim, who is responsible for R&D at eLeaf. Henk, feel free to say a couple of words about yourself as well and eLeaf.
Yeah, so my name is Henk Pelgrim. I got a hydrology degree at Wageningen University, also did my PhD there, and that was already focusing on the use of remote sensing data for estimating evapotranspiration, ET data. So afterwards, I worked as a research fellow at ESTEC for 2 years, and then I joined a company which then was called WaterWatch, which was founded by Wim Bastiaanse, who developed several ET estimation algorithms. WaterWatch was then merged together with another company in the Netherlands, Basfood, to form eLeaf, and that was in 2009. And I've been working since 2002 for basically WaterWatch / eLeaf. And as a company, we focus on the use of evapotranspiration data for water management, farmers, and we produce the data on different scales, so field level up to continental level. So that's I think that sets us a little bit apart of the rest of the companies. Yeah.
Super, thanks, Henk. And finally, we've got Andreas Brunn, our own Andreas Brunn from Constellar. Do you want to say a few words?
Of course, thanks, Cassie. So I'm Andreas. So I originally have a degree in geography from the University of Würzburg, and a PhD in remote sensing from the Technical University of Clausthal, all in Germany. So after that, I had a few stations working on data processing, data calibration, validation, mainly first for the Rapid Eye constellation, later also for the SkySat, data for Planet. After that, I was working for EUMETSAT, basically as a consultant for EUMETSAT, working on YASI and G data. And since a few months, I'm trying to support Constellar, and will be responsible, or I am responsible for the data at Constellar. So how we will process the data, how we get temperatures out of the radiances, how we get radiances at all, and how we get the radiances rectified. So this is my role at Constellar now.
Thanks, Andreas, and I know we'll hear a little bit more about that later on. So thanks again, everyone, for joining. Just for those people who came slightly later, I've made everyone a participant, so feel free at any point to turn your mute off and your video on and chat directly into the conversation, so ask your questions and so on. No obligation, there is a chat channel as well, but feel free to. Also be aware, please, that this session is being recorded. Isa has told us, just in case you do want to turn your video on or off or anything like that. Okay, so the title, as you know, of the session is Heating Up Fast, Why Land Surface Temperature Data is So Hot Right Now. We believe it's hot at Constellar, of course. We're sending up microsatellites into space to measure the land surface temperature of the planet, and we see lots of opportunity, lots of different applications for that data. So without further ado, we've got about 50 minutes left in the session, just under, and I would like to hand over to Pavel to go into a bit more detail about some of the things you've already introduced. Thanks, Pavel.
Awesome. Thank you very much. So I don't have like a super formal presentation here, but everyone can feel free to jump in at any point if you have a specific question, I suppose, about something I bring up. We'll keep it brief if you do jump in. So essentially, we've been using thermal data for quite a while. We probably, before we even started NXT Farm, we were already experimenting with it and doing some contracts, playing around with the data. Everything is based off of evapotranspiration for us in agriculture. That's the fundamental measure. I'm sure Hank is infinitely more familiar with the nitty-gritty of evapotranspiration. One of the big things that we do is actually take that evapotranspiration data and throw it into models, into predictive, essentially, algorithms for trying to determine specific use cases for our Canadian farmers or American farmers that we work with a lot. So one of the really exciting use cases for us with NXT Farm that we discovered early on was using evapotranspiration data in conjunction with soil moisture probes. The reason this was so interesting is you would essentially have your soil moisture values in an area. You'd know if it was adequately wet in the soil, and then you would overlay that with actual evapotranspiration data. And if you saw, for example, the crop water stress increasing in an area when your soil moisture levels should still be adequate, we would generally correlate that to certain crop diseases. So we got very good at picking out root and stem diseases, specifically things like white mold in soybeans here in Canada, well before certain other algorithms were able to pick it up. NDVI being a pretty big one that all farmers here would try and use to determine issues in their field. We could see some of these issues 1 to 2 weeks earlier than they were seeing it in the NDVI. Really exciting for us because things like white mold are actually treatable, and you can go out there, spray your field, and save your crops. So that was something we really doubled down on early on, and we set up a whole alert system around that. And of course, this thermal data was the basis of everything we were doing around there. Stepping off from there, we also were involved in working with cover crops. That's something that's really not used very frequently here in Canada. Specifically not in the prairies. I think we have less than 1% adoption rate of cover crops, but there's a serious value to having cover crops environmentally, in the sense that you have a bunch of carbon actually stored there. It's keeping the soil healthy, but also even for your crops that you're growing tend to be more resistant to drought and to flooding because the cover crops essentially act as a damper to mitigate any effects that you're having there. So one of the big uses for us was taking this thermal evapotranspiration data, going back historically to when they had a large drought or flood, and comparing a field with cover crops to one without. And you can clearly see that you get about say, depending of course on the extremity of the drought or flood, you can get about an extra week potentially of survivability of crop out of fields that were properly cover cropped and matched up correctly with the crops that were growing there. So that's actually one of the mechanisms that we were using to graphically show farmers here the potential value of it. And we've been slowly working on converting them. As you can imagine, with the current work I'm doing in the whole carbon market side of things, that fed right in there, since carbon or cover crops are pretty big in terms of being able to sequester more carbon. So we're trying to convert farmers into doing that, but we're now also using this thermal data as a way to help assess carbon content. And this is a really exciting point to me, and I think Constellar would find this quite exciting if everything pans out the way we see it. Essentially, we are factoring in this evapotranspiration data into models that are calculating out the carbon cycle. Traditionally, and what's currently being done in Canada, they use just fixed variables for all these model specifications. So let's say you know your general environment in an area, let's say in Saskatchewan, they would plug in soil type, they would plug in crop type, growth stage, and you know how much soil radiance they expect, and all these kind of features into the model, and then calculate it out. But we know for accuracy's sake, even within one field, there's insane variation in what actually happens there. You know, there's going to be your soil type sometimes change in a field, you have different topography changes, your crops are just going to grow differently based on how that field looks. And if evapotranspiration is going to be one of those key indicators as to how that whole carbon cycle is moving. So we are currently using that evapotranspiration map, factor it into these models to essentially give us spatially relative like carbon contents. Right now, of course, we can only use Sentinel-3 and Landsat. Issues there with the resolution. It's still better than just winging it for an entire region, but there's some pretty drastic improvements when being able to look at specific variation throughout a field. So with the obvious improvements in quality there, that would be the choice long term, in my opinion, to use for carbon calculations that all these countries are going to be doing in order to assess how they're currently performing. And we'd like to make this thermal method a new standard. And that's essentially what we're working on right now, doing tons of test cases along this line, calculating out all the accuracies, and then submitting proposals to the government to get this running. So if we can get more data to, you know, help account for certain variations throughout the growing season, if we can get higher resolution data, that's all very important to us to help increase the accuracy as we keep moving. So that's kind of a summary of how we've used thermal. If there's any quick questions, I suppose anyone can ask, but I'll hand it off to Hank if not.
Now, I've got one question for you, actually, Pavel. What would help you the most? Would the frequency of more frequent observations help, or the better spatial resolution, if you had the choice? That's
Yeah, it's a really solid question, and I think it's definitely going to be the more frequent data right now, specifically because we land on a few cloudy days way too frequently. And in agriculture, as I'm sure you're very familiar, sometimes you have, you know, a month of peak development and you really would like to capture some data within that month. So just having some more frequency and a slightly higher chance of getting non-cloudy data would be incredibly valuable.
I would have a quick question, Pavel, as well, because I know there are many companies moving into the carbon space, and particularly looking at how, you know, farmers can generate income, for example, from carbon credits and etc. How fast is this race kind of going? And, you know, I understand at the moment it can be quite confusing for farmers to navigate the whole sort of carbon credit system, understanding how they can move from samples through to using, for example, satellite data, etc. Also understand there's a potential lack of granularity in some of the data that's available. How do you sort of see that market shaping up, and how quickly will it be, let's say, mature?
Yeah, it's definitely a challenge for most of the reasons you mentioned there. I'd say the two biggest are, you know, farmers having the difficulties understanding how to use the data, but also the reliability of the data coming to the final purchasers. So if you're buying a carbon credit, every carbon credit is not equal. And traditionally, for example, Alberta had a protocol that involved no-till. So if you stop tilling your field, every single year they would pay you carbon credits. which, if anyone's familiar with carbon cycles, is pretty ridiculous because as soon as you actually till, all of that carbon's out in the air again, and you've now paid someone for doing absolutely nothing. So that makes some of these early stage credits very, very, very unreliable. But I would say there's a big move right now to get more farmers on board. Here in Canada, they're very interested in figuring this out because of the carbon tax that's inevitable. The US doesn't really have that problem, but farmers here have been reaching out to us inquiring about this. So I think to set up some basic protocols for them, that's within the next year is going to be pretty widespread amongst farmers. To really dive deeper into it and discuss 10 15 different methods for them to change things may take some more time, but for sure, like nitrogen management for them, no-till and cover crops, I'd say 1 to 2 years most Canadian farmers are going to be using that pretty extensively to help offset any carbon tax that they're paying.
Okay, thanks, Pavel. Does anyone else want to jump in with any direct questions? Otherwise, feel free to come in at the end when there's an open discussion.
I might have one for Pavel. So what is the current cadence you get data from, and from let's say Landsat? How much data do you get for your areas, taking into account cloud coverage and 16 or 8 day revisit time? And what would be? I mean, the ideal is clear, but what is the number which would really help you?
Yeah, great question. So, like, as you can imagine, of course, it like really varies based on the area. Saskatchewan, love working there. It's relatively cloud free most of the time. So 16 or 8 days, let's say we get 80% of the images that we'd actually get would be good. And that's sufficient, I would say, for what we do. Most of the time in peak growing seasons, we have enough data to be able to run, but that's a very specific province for us that isn't very cloudy. As soon as you go over to BC or Ontario, which are quite a bit cloudier and have more high value crops, more ability to actually sequester carbon, and are generally more dynamic regions that need the measurement more, they're the ones that have more cloud. So I would say we're losing probably around half, if not more than half, of the actual images that are coming through to us, which is very not ideal. We've actually used Planet before for, of course, different purposes, not for thermal applications. But we found that when using Planet, we can usually get one cloud-free image per week. So there is a potential to get weekly imagery, assuming you have higher frequency revisit times. So if we could shoot for an image a week, that's already quite a bit better, and especially stacked on with Landsat, than shooting for 8, 16 days or things of that nature.
Okay, cool. Thank you.
You may have noticed I've just added a few more people, so just so that everybody's not alarmed, I'm just going to repeat myself a couple of times probably. So I've made everyone an active participant. This session will be recorded. There's no obligation to speak, but if you do have questions and would like to participate in a discussion, then feel free. Otherwise, the chat function is there as well. Thanks. Okay, so Henk, if that's okay, I think I will hand over to you. I know you've got a couple of slides to share. We can't hear you at the moment.
Yeah, try to select window. Just a moment for sharing. I think we now see. Let's see.
See the screen, but not your slides.
You see the slides? That's
No, not yet.
Oh. Then I need to do something else. That's well, last time it worked. That's still no slides, I think, or.
No, we are just seeing your WebEx window.
Okay. Let's see. No, well, stop sharing. I will try again. It's working a bit slowly.
No problem. In the meantime, if anyone has any other questions for
Yeah, feel free to ask.
jump in.
There is a question from Ben in the chat, Cassie.
Oh, thank you. Yeah. Okay, so I'll jump in then. So how important is ET, so evapotranspiration, for modelling carbon sequestration compared to monitoring crop cover or crop type, cycle, tillage, etc.? Pavel, do you want to answer that briefly now, or should we take it to the end now that Hank's slides are?
I think we can save it till the end. Shouldn't be a huge rush.
Then we'll come back to you, Benjamin. Thanks for the question. So Hank, feel free to.
Yeah, I managed to work it out. That's okay. Thanks. So I've got a short overview on the types of things that we do with thermal infrared data on at eLeaf, and mostly focused on the water management side. So basically, what eLeaf does is we produce two major data components. One is the water consumption, which is actually the evapotranspiration data. The other one is the biomass production. So the amount of crop that is grown, and the other side is how much water is this crop or this land surface using. And as we can see that we have a few different scales on where we produce our data. So it goes from continental, so that's the whole of Africa and the Middle East, unto the national, and in this case it's South Africa, to regional and field level. And then basically we do it for every pixel, and field and regional, that's more or less 10 to 30 meters. Depends a little bit on the sensor that we use. Continental and national scale is usually done on 250 meters or a kilometer. So what kind of thermal infrared data do we use now currently? Well, currently it's Landsat 7, 8, and well, 9 is also not operational yet, but it's has been launched, I think, 2 weeks ago. So that's something that we really expect in the near future. Those are for the high resolutions. So that basically that's the highest resolution that you get outside of EcoStats, of course, but that's the 100 meters. And the medium resolution are then provided by MODIS, FIRS, and Sentinel-3 at the moment. Short overview of the history of ET mapping within eLeaf. So we started as WaterWatch, and it was basically our first ET algorithm that we used was Seaball, which was published in 1998 by Wim Bastiaanse. That we used that for approximately 10 years, and until I think 2015, we still have projects which were using Seaball. Seaball's really good at mapping ET for smaller scales and also for local scales. So if you would go beyond a single Landsat tile or a single Sentinel tile, then you need another type of algorithm, and that's been ET-Look for us in the last 10 years. So that's because certain things we couldn't solve with Seaball that we could solve with ET-Look, and that was the problem of making an ET map for the whole of Africa. So that was started in 2009. So there was a need for an algorithm for all areas, and so we now use ET-Look for the small scale up until the large scale. We can do it on daily time step. Now, well, it uses thermal infrared data but also optical data. We can do a long time series, multi-seasonal or multi-yearly. Well, and there was ET-Look is now being used also by the FAO as the algorithm to use for the WAPOR portal, which is the water productivity portal set up by the FAO. So this is an example of the WAPOR portal. So this is for an area. So WAPOR is a project set up by FAO to provide their users with an overview on ET for the past 10 years. So from 2009 until now. So it's still operational. So we produce every decade, so every 10 days, maps of ET for on the low resolution on 250 meters for the whole of Africa, on 100 meters for the large watersheds, but also 30 meters for very specific small irrigation areas. And you see an example of that here. This one is in Senegal. Well, they set up, so we deliver the data, they provided the portal. So this is the portal run by FAO. Well, you can look at time series for ET over the season. So you see here the difference between the dry hot season where there's irrigation and the winter season where the crop growth is dependent on the rainfall. And if you also compare that with the precipitation information, which is also there, then you can see that, well, the second cycle of growth is then determined by rainfall. So ergo, the first one should be is decided by, or is governed by irrigation. So how do we add value to these ET maps? So what we try to do is understand and quantify the spatial and temporal distribution. I think the spatial component is the one thing remote sensing data is very good at, to see spatial variability within fields, within countries, to see how it's used, but also see trends throughout years, and basically also detect anomalies which are out of the ordinary if you look at a normal season compared to a dry year or a wet year. And well, the challenge is to translate those data into actions, actually, that people can perform their management or make arbitrary actions or informed actions, actually, on using for their purpose. So be it a water manager or be it a farmer. So there can be a large range of potential users. Now, if you look at the water services that we have in eLeaf, then basically these are the categories. So it's the water distribution, so crop water demand forecast, basically trying to get an idea on how much water is needed for the coming week in an irrigation schedule, in the irrigation system, water monitoring. So basically how much water is used where and by who. Water auditing is quite interesting here because that then links the water use by the farmers also to how much water they are allowed to use. So that can be used as a monitoring tool and also as a tool to inform farmers that they use too much water for that for their purpose. Crop production, so the WAPR is being set up as a water productivity. So how much crop can you produce per drop? But also on disaster monitoring. So what is the impact of droughts and what's the impact of floods on agricultural production, but also on irrigation systems. Now, we have two platforms running actually on those. So FieldLook is looking at farm management services. We have a special case in South Africa, which is called FoodLook, where we look at fields in the Western Cape province in South Africa, and it's free service for food farmers, and that's being funded by the Department of Agriculture. Well, and also this data is then also be actively used within those areas, so they can have better informed management decisions based on our data, so that they can use either less water or improve their yield with. And if we look at the farm management itself, this is for sugarcane. We can do a variety of services for sugarcane. We can look at difference within fields, but also try to forecast the yields and see if they match up with measured yields at the mills itself. But also looking at the logistics of sugar mills. So they want to know when they can harvest which plots at which times, so that they can improve their logistics based on the things that we see with satellite. But Pavel already also mentioned that sometimes early warning can be very useful by using thermal infrared data, which picks up at least problems due to water stress earlier than optical signals. So the thermal infrared data is really sensitive to a lack of soil moisture. So in this case, we have water logging. So there's actually too much water in this area, which hampers the growth. And here we are looking at the large-scale irrigation systems where we can detect how much water is being used, but also together with some information on weather forecast data, also can forecast the water demand so that they can manage their systems better. So if you look at the whole time series through a year, then when they can see when there's a peak demand in water. So that also is that has to do, of course, with the growing cycles itself, but also the availability of water. This is a case in Morocco where we see that where we can look at how much water is available and then for rainfall, but then also compare it to the actual evapotranspiration, so they can see which farmers are using quite a lot of irrigation water. And for them, it's a way to make informed decisions before they go into the field, so they know which farmers are then. They have to speak to them to see if they can improve their situation, or see if they're either lacking water or have used too much water. So here, there's one of the testimonials there that it says that it helps them to optimize their trips in the field because also they have a large area to cover. Lastly, the water auditing, so that it is basically to check how much water is being used to allowed water quota. So in this case, then the graph on the right, you see an allowed water allocation. And in this case, the farmer uses less than it's allowed. But in this case, and the other one option is also possible. So we have a cooperation with another Dutch firm, Hydrologic, which makes this platform for the water use associations in South Africa here, and they can then check to see whether the quotas are met or not, and they use it as more as a warning system. So that it's not a fining system, so people don't get fined, but they get warned ahead of time if people can see that they are using more water than there have been allocated to, because you can monitor throughout the season and see then at which point you can expect to have an overdraw. And also this is also more on this is Tanzania, to see to have for water managers. It's quite important to also have an overview on where your water is used for which purposes. Because for them it's quite difficult to because they monitor, if they are responsible for a large area, but they also want to know where are the problems. And what I've said before, spatial variability is that's a nice thing that you can measure with remote sensing. Lastly, this is an additional product where we just look at the mapping, actually, or the irrigated area mapping. And this is for Morocco, where we're interested in where there was some changes in irrigation of area used for irrigation. So some areas were taken out of productions and others were taken into production. And it depends a little bit on the local situation there. So that was basically a short overview on the type of applications that you can do when you have ET data, which, for us, all ET algorithms that we use extensively information from the thermal infrared satellites, or the thermal infrared sensors on satellites. Again, Probably
Okay,
stop sharing.
Yeah, cheers. If anyone has any direct questions, feel free to jump in.
Let's see.
Yeah, Hank, so I was curious. Why do we have an echo? Does anyone else hear an echo, or is it just me?
I don't have an
Maybe
echo, but
everyone else can just mute themselves a minute.
I'm gonna assume it's just me. No, that's perfect. Okay, so question for you in regards to irrigation. Have you ever worked with variable rate irrigation in places like California that have, the center pivots that actually spray at different rates?
I think that's already quite a long time ago that we actually we did some work in California, and that had to do with variable rate, but that was, I think, in the mid, I would say 2005, 2006. The problem is that because the summer infrared data comes only as a snapshot. So especially with pivots, well, they have I'm not sure if it's a daily cycle, but it's a cycle which takes quite a long time. So basically, what you see within these pivots, that the area that is just passed is well, the ET is much larger than the area which was passed a few hours ago. So it's quite difficult to use that instantaneous data to get an idea on the applicability of variable rate. So I think we looked at it, but we didn't use it in an operational way. It was just more to see what we can do with it. But
Yeah, very fair. I just know on the planning side of things, I've heard of some of them using, there doesn't seem to be a very standardized way for coming up with a variable rate irrigation plan. Some of them use topography, others just more previous yield maps. So be curious if there was a way to optimize that a little bit more.
I would say that actually there should be, but that's and usually those pivots are quite homogeneous. I would say that it's more likely to have an impact in other types of irrigation, but that's usually more difficult to apply variable rate then. But that's
There's maybe someone else on the call later who might even be able to answer the question part. Okay, in the interest of time, I'm going to move on to Andreas, and then if there are any other questions, we'll collect those at the end and have a bit more of an open discussion. So, Andreas, if we can try and keep it to about 10 minutes, and then we've got about 10 minutes left for Q&A.
Okay, can you see my screen?
yes.
Okay, cool. So for all those who have joined the session before, there will be so you might have seen some or most of the slides before, but I want to just give a little bit of an answer, or maybe present a system which might make the life of Pavel and Hank a little bit easier in their jobs. So this is what you can expect from the future Constellar constellation or constellations, whatever you might call it, or how you might summarize the different ones. So this is again the roadmap actually. So what we are currently are distributing data from current missions like Landsat, EcoStress, and stuff like that in our heater pipeline, and the heater pipeline will be added by the IOD space pilot project, which is going to launch to the ISS on the 31st of January in the next year, and we expect to have some data available then end of February, end of March from this mission. So the real satellite missions, which I will describe in the following a little bit, is the constellation Generation 1, which is built out of one pilot satellite, which is coming early to mid 2023, and the rest of a 4 satellite constellation then coming towards the end of 2023. In early 2025, we are planning to get the next constellation up, which means not a really new constellation, but a set of new satellites adding to the constellation, also at a different time of the day for imaging. I'm coming to that later in a little bit more detail. And then 27, the next set of satellites, and the ultimate goal is planned to be fulfilled so at the end of 2028. So the Hive system basically consists of course the microsat constellation, which is a space segment which has for the beginning 4 satellites with vis near and TIR payloads. We will operate our own ground segment and the data processing segment. We will have our user segment, which is all the processing stuff onto land surface temperature data, and we will also provide a user API and a web user interface for customers to get our land surface temperature and land surface emissivity data out of the system, and do some data aggregation and get some insight out of the land surface temperature data to provide the information to end users like insurances, agriculture, governments, trading, research, everything. So a few words about the Hive constellation. So as already said, so the first set of satellites will come in 23 and 2024, which will be probably 7 with near bands and 3 thermal infrared bands with a spatial resolution of 50 meters in the TIR and between 10 and 20 meters in the visible and near infrared. We will get 4 identical satellites in the sun-synchronous orbit. We will have daily coverage of any point on Earth. So that doesn't mean that we are imaging the whole Earth every day, but we will have access to any point on the Earth on a daily basis. What I see from the presentations before, we will have the data at the same time of the day, which seems to be an important thing. So for the first set of satellites, or the first constellation, we will have that at around 2:30 in the afternoon. We will launch a second, more or less identical satellite constellation in 2025, which will deliver data at a different time of the day, probably earlier, let's say at around 10 in the morning, so that this allows to optimize for the cloud coverage. For example, in the tropics, it will be useful to have the data earlier in the day to have a better chance to get cloud-free data. While in some desert regions, it will be better to have later in the day the data, so that all the morning fog has been cleared or has cleared. So about the spatial resolution, a little bit of a comparison to what we have today. On the right side, so this is the 400-meter resolution range data which comes currently from systems like MODIS or VIIRS, and which is twice a day available. On the left side, we are seeing the Hive image, which will have around the 50-meter resolution, which comes also twice a day in, let's say 4 years. So I think this will be a pretty good improvement. And talking a little bit more about the temporal resolution of the system, which we will get. So we will have a daily revisit time in the sun synchronous orbit at 2:30 from the end of 2023. We will have twice daily with an additional morning orbit in the full constellation set up then. So the sun synchronous orbit allows for comparable data at the same time of the day. So I don't need to adjust for different times of the day, which is always a little bit vague, maybe, or at least highly dependent on the area. So I need pretty good knowledge of the area I'm working on, if that works at all. So the daily revisit time and the daily twice revisit allows for a pretty high cadence, even in cloudy areas, and it increases the probability of free data in different regions, of cloud-free data in different regions. So talking about the time, we can discuss a little bit. So if you have further questions, I'm happy to explain a little bit more. So I'm ending here with the first image out of our lab window from the camera, which will go onto the ISS in a couple of months. Oh, thanks a lot. And if you have questions, feel free.
Thanks, Andreas, appreciated. Any quick responses, questions right now?
I would just say I'm very excited for it. One of the things that stands out to me on the spatial resolution side of things is because you're getting true 50-meter resolution. That's really going to be a big factor for us in terms of crop disease. Like currently, crop disease will start forming in a few plants. And working with anything 100-meter plus, it's very, very hard to figure out where exactly that issue is happening. And a lot of the time it'll average out. You won't even notice it in the pixel. So the 50-meter could well be a pretty big game changer in terms of early detection of diseases forming. So very excited for that.
Yeah, thanks, Pavel. Good point. Okay, so what I will do now is ask Benjamin's question, since he's been waiting patiently, I think, for an answer from Pavel. So yeah, I guess, Pavel, you can read the question there, but just for everybody else, perhaps. So how important is the evapotranspiration for modelling carbon sequestration compared to monitoring cover crop type, cycle, and tillage, etc.?
Yeah, absolutely. Definitely a great question. So we still will be monitoring crop type, the actual cycle, and tillage. The big differentiator with using ET is you don't actually need that initial ground truth data, ideally. So the way existing models work is you would start with soil sample data, you would quantify how much carbon is currently there, and then when you actually apply these techniques based on what your previous practices were and how much carbon you currently store, then you can start calculating out how much is added on. And that soil sampling, the initial assessment, is really, really expensive to do and limits the scale. Whereas when you're actually looking at evapotranspiration based on those rates and based on, the soil type and all these things that you can pull remotely as well, then you can actually start interpreting how much carbon is stored, which if you can remove the soil sampling aspect or at least reduce it significantly, that will be a massive cost reduction for us and, of course, allow for actual global usage of this kind of technology.
Thanks, Pavel. We've got a couple of other questions there, one or two probably directly to Andreas. So what kind of VNIR capabilities, bands, etc. Will be foreseen? I don't know, Andreas, how much you actually want to and are able to say here.
I'm also not really know what I'm allowed to say here, but I can say what I know.
Exactly.
So with new capabilities, we are talking about 7 bands in the visible red edge and near infrared range. We also thinking about a yellow band. This is in the final stage of definition at these at those days. The GSD is better than 20 meters. So actually, the foreseen camera would be capable of doing 6 to 8 meters, but in terms of data amounts of data and our needs. So basically, the Visneer is made for supporting the level 2 processing of our own data. So we will probably have that resampled to 20 meters in the final product, just for getting comparisons to the, or better comparisons and better support to our thermal infrared data. Also,
Andreas,
yeah.
Sorry, quick question in between. Will this then also be flown on the ISS? And
no, Visneer will not be flown on the ISS. So on the ISS, we just have a camera, which has 2 bands at around 10 and 11 micrometers, which is just a pilot project where we will derive land surface temperatures calibrated to ecostress. Okay, I see the next question, which is probably also for me. What is the swath of Constel R to achieve a daily revisit? It will be at around 80 kilometers. It is also not finally defined yet, but we are talking about a swath width of 80 kilometers.
Excuse me, this is Benjamin. Can I perhaps just shortly follow up on that? You mentioned 4 platforms with 80 kilometer swath. How do you get daily revisit? Is that
so? The plan is not a mapping system which which does everything every day, but together with the agility of the satellite, we can point it to any point on Earth every day.
That I understand, but you also made the point that you want to have the same overflight time, and that would then kind of
it makes the overflight time not by the minute, but for solar time, it is still pretty close.
Okay, I mean, I'm just wonder how that works, because we have done a lot of studies on that from the LSTM mission. I'm the mission scientist of the LSTM.
Okay.
Also happy, Benjamin, if you do have other questions, we can perhaps arrange a call offline and discuss that in a bit more detail if you have specific questions that we might not necessarily want to go into too much detail about some of the requirements of the technology here in the call.
I think the revisit is quite interesting, but that also means that if you want to have a revisit time of a certain area, that you have to order that area beforehand, or in order.
Yes. Yes. So we will expect orders, and of course it is true that the constellations due to the pointing capabilities. I mean, there will be some minutes. I would say difference between today and tomorrow due to the different orbits.
Okay.
But it is not the difference between, I don't know, 9:30 and 10:30, but we are then for an area at between, I don't know, 2 and 3 or something like that.
But it also means that you are looking at a certain angle then, instead of
yes.
Okay. Which opens up quite interesting things, actually. But that's.
Yes, absolutely. So Peter just noticed that also in the chat. Yes, we will have to deal with viewing angles and also BRDF effects and stuff like that.
Yeah, but there's also quite some signal, I think, if you're looking from a certain angle instead of nadir. That if you look at the plant from from 30 or 60 degrees, that makes a difference also, and that says something about the amount of leaves available, and that could be actually a plus.
Yeah.
Might jump in with a question for you, Henk. You mentioned in one of your cases, I think it was the South African case, that there was a reported 30% yield increase in one of the projects that you were looking at. And I'm conscious also from our perspective as Constellar that it's often very difficult to address the end user when we're not sort of directly speaking with farmers. So I wondered what experience you've had of how best to sort of directly and effectively address farmers and their specific needs, particularly in some of your African projects.
Yeah, so basically what we are good at is monitoring. So it's also always the case to how to address what you see, try to and that's always with aid of the end user itself to make sure that so what they see they also can use in their management to improve their current situations, either their water use or their yield. So what we can provide is the data. What we always have to do together with clients is to make sure that the data is translated into to actions to improve their management. And that's always something that you have to do together with the end user. There's no golden egg or there's no golden solution for anybody everywhere in the world. So that's I think also one of the more interesting parts of the business to see basically that your data is influencing people to take actions and.
Absolutely. Pavel, any comments or questions?
Yeah, I couldn't agree more with Hank. Pretty much in agriculture, no one wants to look at a satellite image and figure out what to do from there, at least in our experience, unless someone's super technical. Even the agronomists that we service, you have to give them a distinct call to action with each one of these pieces of information. So you have to figure out how to derive it and tell them what to actually do from there. Obviously an example with our crop disease prediction, like we give them a heads up early on, we highlight it in their field, and then they can use their traditional methods to go out and deal with it. So there's definitely a layer of processing that needs to happen. So I think from Constellar's point of view, if you can just get that integration between people like us and yourself to be as smooth as possible, then it'll really help us actually service these farmers directly.
Okay, so I think we don't have any more questions in the chat, but if anybody as a participant has a direct question they would like to pose, then please feel free. Otherwise, if there are questions between the panelists, then we've probably got space for just one more, and then we need to call it to a close.
I don't want to steal the last slot, but I might.
Please do, Andreas.
For Pavel and Hank. So at least Hank talked about using MODIS and VIIRS. So taking a MODIS or VIIRS image will also lead to pretty high off nadir angles at the edges of the images. What are your current experiences with these ones? I know we are talking about a completely different spatial resolution and stuff like that, but I would be interesting now as this discussion came up. I was wondering how you handle this one or how this influences you. You are muted, Hank.
Yeah, sorry. So basically what we do now in our operational processing is either mask out angles which are too steep. If it's, I think MODIS goes from -35 to +35. I think we stop at 20, 25. I'm not completely sure, but But also because then we have daily outputs, and if we aggregate that over a week, basically what we do is assign a higher weight to the observations which are made at nadir instead of looking at the angles. So we assess basically the quality of the data itself and use that as a way to aggregate results over a week. So and that's something you can do if you have a daily revisit time, and that's really helpful. But I think the future is quite bright. I think for lens surface temperature. 10 years ago, the situation was much worse actually, because I think even for Landsat there was at some point in discussion to remove the thermal infrared sensor due to the costly. I think the cost involved with thermal infrared is higher than with the visible and near. Basically, they had to convince the USGS and to include that, because it was one of the use cases they presented was the EVA transformation. So that's so there's a big change coming on, and that's really nice to see.
Super. Any final
Good, thank
questions?
you.
No, in which case then I would like to thank everybody for joining, of course, and particularly the speakers, so Andreas, Henk and Pavel, thank you for joining. If anybody has any other questions that they would like to ask, maybe outside of this forum, please feel free to contact us. Each of you feel free to put your contact details in the chat, and then people can reach out to you directly if you would like, if you haven't already got the email address from the slide deck. Otherwise, once again, thank you for your interest. If you have any other questions, then please reach out, and we wish you a nice evening. Thanks for joining our session.